Hello everybody and welcome back to another Big Ideas Algebra 2 lesson. Today we're going to be talking about section 3.2, which is on something called complex and imaginary numbers. Now, this is going to be likely the toughest section in this unit. There's a lot of new thinking we need to do with a number system that we've never worked with before. So, as we're taking notes here, I want us to make sure that if we need extra practice, you can come talk to me, you can come find extra practice on Big Ideas. If you need extra practice, take that extra practice. There's my recommendation for this section. So, what are we talking about today? Well, we're talking about different types of sets of numbers. For instance, there's positive numbers that exist. There's negative numbers that exist. There's fractions that exist. There's a bunch of different ways we can describe different groupings of numbers. At the very bottom of this tree, right down here, we have something called the natural numbers, or the counting numbers. This is where the natural numbers are. And the natural numbers are things like 1, 2, 3, 4, and so on, so forth. The natural numbers are just the numbers that you use to count on your fingers and toes. These are the numbers that you learned in elementary school, the natural numbers. But we know that there are some extra numbers that we have to add into this set. For instance, we know that there's not just these numbers here in the positives. Above that subsection is the whole numbers. Whole numbers are still counting, 1, 2, 3, 4, 5, but it also includes 0. So it's 0 through infinity, basically. The reason why these are two different sections is because 0 wasn't discovered until much later in math's history. Before then, we just didn't have a number for it. So 0 is a part of the whole numbers. The natural numbers are called a subsection of the whole numbers. Think of it like this. If we have on our sheet of paper here, let me actually turn this sideways because it's going to get very big very quickly. If we have a circle here, or we'll make it an oval, that represents all the whole numbers, so that's 0 through infinity. Well, there's a tinier subsection, or smaller group of the whole numbers, right here, the natural numbers. And that's just 1 through infinity. You see how the whole numbers also has 0 in it, but the natural numbers don't? That means that all natural numbers are whole numbers. Beyond the whole numbers, though, we start to get a little bit more fancy. Because these only count positive numbers. We also know that negative numbers exist, so we have a word for those. The integers are any numbers that are positive or negative whole numbers. So it's positive or negative whole numbers. So this includes things like -1 and -20 and negative infinity and 0. So we go one level up to the integers. And again, all these other bits are subsections of the integers, or subsets. Because the integers have numbers like 1, 2, 3, 4, 5, 6, 7, but they also have the negative versions. The integers have the positive and the negative whole numbers. So the integers are a little bit bigger of a group than the whole numbers, because now we have negative numbers in there too. You see what we're doing? We're basically constructing different groupings of numbers. Sure, we can do math with just the natural numbers, but you can do more math with whole numbers and more math with the integers. Once you have negative numbers, you get to do a whole lot more. Now, where do we go from here? We've got positive whole numbers. We've got negative whole numbers. What else can we express? Well, fractions and decimals, of course. These are called the rational numbers. And we say that rational numbers are just basically fractions, or anything that can be written as a fraction. Decimals, for the most part, can be written as fractions too, right? The rational numbers are a bigger section than the integers because it includes your fractions. But there are some numbers that are decimals that can't be expressed as fractions. Think about it. You ever heard of a number that starts something like this, for instance? Maybe it starts with, I don't know, 3.141592653, and it goes on forever and ever? Yeah, pi. Pi cannot be expressed as a fraction. You can get pretty close to it, but pi can never be expressed as a fraction. Pi isn't a rational number. Pi is something that we would call an irrational number. An irrational number. Irrational numbers are decimals that can't be fractions. Decimals that go on forever and ever and ever that cannot be represented as fractions. So like 1/3, that's 0.33333, that can still be represented as 1 over 3. But pi goes on forever. You can never express that as a fraction, so it's irrational. Well, this is a problem. Rational numbers are the next step up from the integers because it includes all your fractions, right? But irrational numbers would not be in this bubble. Once again, our rational numbers, or our fractions, we'll say n over m, these are different than the irrationals, which cannot be expressed as fractions. So we'll set a little bubble aside for the irrational numbers. Like pi, or the square root of 2. Now, here's something you might have heard before. When something is a solution, or when something has all solutions, even infinite solutions, you might have heard the phrase, all real numbers. You ever heard that phrase, all real numbers? Well, the real numbers are basically every number we have ever dealt with in our life. That includes rationals, that includes the irrationals, that includes 0, that includes negative numbers. Every number that you have dealt with up until this point was a real number. The real numbers is basically any number that we have ever learned up until this point. But there is also an opposite of the real numbers. Something that we're going to be talking about today is a subset that is outside of the real numbers. It's called imaginary numbers. And don't worry, it's not like made-up numbers. It's just numbers that you wouldn't be able to point out on a number line. It's numbers that don't follow a natural order. It's numbers that we think should exist, but just don't. We'll talk about this in a moment. But the main idea is we now have 2 more bubbles. The bubble out here will represent our real numbers. Our real numbers. But, like we said, imaginary numbers are outside the scope of real numbers. Imaginary numbers are numbers that really wouldn't have existed otherwise. Imaginary numbers go right here outside of the real numbers. So we've got real numbers, which is everything we've ever learned up until this point, and then imaginary numbers, which we're going to learn today. There's only one last thing. If you ever wanted to add or subtract a real number and an imaginary number together, maybe 3 plus one of these imaginary numbers we're going to learn today, you would get something a little different. It's not real, it's not imaginary, but it has pieces of both. We have one last section to represent all of those numbers, the numbers that are made up from a real part and an imaginary part. And these are called the complex numbers. Complex numbers are those numbers that have a real part and an imaginary part inside of them. So complex numbers go at the very top of our tree. So this is the number system that we all know. At the very top, we have the complex numbers, which have a real and imaginary part. Real numbers could be rational, so they can be written as a fraction, or irrational, meaning they go on forever. Rational numbers could also be integers, which are positive or negative whole numbers. Some of those integers, the positive ones and the zeros, are called whole numbers. And if you remove the zero, you get your natural numbers. These are all the subsets of these selections. In addition, there are symbols to represent all of these. You will not need to know any of them aside from the real number symbol, but it's kind of cool to see the other ones. The real number symbol is something that we've seen before, actually. It looks like this. It's like a bolded R. This is what the real number symbol looks like. Let me draw it out a little bit bigger. There we go. But there's also a symbol for the complex numbers. It's a C with a line like this. There's a symbol for the rational numbers. The rational numbers have the symbol Q with a line through it, which stands for quantity. The integers have a symbol as well. It's a bolded Z. So it's like a Z with two lines in the middle. The whole numbers have a symbol, and the natural numbers have a symbol as well. For the whole numbers, we could use a W, but I think the actual proper symbol for this is like a bolded N with a 0 under it, whereas the natural numbers are just a big letter N that's bolded. Of course, there's also symbols for the irrational and imaginary numbers. However, there's a lot of mathematical debate about which symbol to use for these, because both of them lay claim to a bolded I. In general, though, the set of imaginary numbers isn't really that comprehensive, so we like to use the C to represent it. I usually goes to the irrational numbers. So, it's about time we start talking about what imaginary numbers are. We've mentioned them a lot at this point. Well, let me give you an example here. Let's say I asked you to find the square root of 4. Well, it's actually not that crazy of a question. Most of us know the square root of 4 is 2. That's just an integer. It's a real number. Both of these end up being real numbers because they simplify to a real number. But if I asked you to find the square root of negative 4, even if you plug it into a calculator, it would tell you the same thing. Mr. Strager, there's no such thing as a square root of negative 4. Even though it seems like there should be, right? It almost seems like the square root of negative 4 should be like negative 2, but that's not so. Remember that whenever we square root something, we get a positive and a negative version. So the square root of 4 is positive and negative 2 already. The square root of negative 4 can't be negative 2 because negative 2 times negative 2 is positive 4. So what gives? Well, we remember that there was this trick that we learned, a way of splitting up square roots into their component parts. Let me refresh your memory. When we had problems like the square root of 20, which we said, oh, there's no way that has a real answer, we split it up into two numbers that multiply to make 20. So we could split up into the square root of 4, for instance, times 5, which we know simplifies to the square root of 4 times the square root of 5. We can split it up. And the square root of 4 is just 2. So we were able to simplify a number that seemingly had no solution by splitting up into its multiples. Into its factors, I should say. Can we split negative 4 into two factors, one of which is a perfect square? Yes, we can. We can split negative 4 up into negative 1 times 4, right? And the reason why we do this is because we know, hang on a second, well, the square root of negative 1 doesn't really have a real answer here, but the square root of 4 absolutely does. It's just 2. So it seems like the square root of negative 4 is going to be 2 times something. We just don't know what that something is, because we don't know what the square root of negative 1 is. It kind of makes sense when you look at it too, right? We know that part of this answer has to be 2, because the square root of regular 4 is 2. We just don't know what the square root of negative 1 is. This is where we start talking about imaginary numbers. Everybody, there is no real answer to the square root of negative 1, so we use a symbol to represent it. In the notes here, there's a little box down here, right here. We are going to use a symbol to represent the square root of negative 1, so that we can still do our math with it, and just remember, oh, by the way, this answer is a little bit imaginary. The symbol we use is just the letter I. I is the same as the square root of negative 1. We use I to show that a number is imaginary. We use I for imaginary numbers. So if you see an I anywhere in your number, you know that it's an imaginary number. So here, we got 2 times the square root of negative 1, right? But we said in our notes what the square root of negative 1 can be represented with. The square root of negative 1, we use the letter I to represent it. So this is just 2I. Now, obviously, we know that the square root of 4 can have a positive and a negative answer, so we should really be writing this as the positive and negative 2I. But this is basically how we simplify it. We get the square root of negative 1 by itself, so we can turn it into this I symbol. We'll eventually learn how we do math with this letter I, but just remember, the I just means the square root of negative 1. So let's take a look down here. Oh, before we do, I want to ask you a quick question. If I is the square root of negative 1, so if I equals the square root of negative 1, what's I squared going to be? Well, think about it. If we square this, it means we have to square the other side too. But what's the square root of negative 1 squared? Squares and square roots cancel out. So I squared is just negative 1. You might see some problems where you'll end up with I squared in the end. And if you do, just remember that I squared is just negative 1. Down here at the bottom, we want to determine which subsets of the set of complex numbers these terms are in. Let me give you an example. I'll take a look at letter B. The square root of 0. What's the square root of 0? In other words, what times itself equals 0? That's just going to be 0. Which of these subsets is 0 in? 0 was in our whole numbers. It's also an integer and a rational number and a real number and a complex number, but we just like to say that it's a whole number. Can you solve the rest? Can you figure out which subsets each of these numbers should be in? Pause the video and try these problems out for yourself. So when we simplify all these square roots, we get the following. What subset is the number 3 in? Well, that's one of our natural numbers. That's one of our natural numbers. What about negative 2? Well, the integers have positive and negative whole numbers, so this is an integer. 2/3 is a fraction, which means that's a rational number. And finally, we know the square root of negative 1 we write as just I. And this is in the imaginary numbers. So remember, I means imaginary. Let's flip the page and let's see if we can go a little bit more in depth with these imaginary numbers. So, the reason why these were invented is because not all quadratic equations have real number solutions. Like x squared equals negative 3 doesn't have a real number solution. Since the square of any real number is never a negative, this would be the x equals positive or negative square root of 3, or square root of negative 3, I should say. To overcome this, we create an imaginary unit I, which we use to write the square root of any negative number. Once again, if I is the square root of negative 1, and we square both sides, we see that I squared is just negative 1 itself. So here's the rule, everybody. The rule here is, if we want to find the square root of any number, we can split it up into a real part and an imaginary part. So for instance, the square root of negative 25, well, we know that we can split this up into the square root of negative 1 times 25. Which we know we can also split up into the square root of negative 1 times the square root of positive 25. Well, what is the square root of 25? That's just 5. And what's the square root of negative 1? That's I. So 5i. Of course, yes, we would also want to write that it's the positive and negative 5i. For the purposes of this activity, we're going to skip that portion, but you're right. Whenever you square root a whole number, you get a positive and a negative answer. So you should get positive and negative 5i. For the rest of this page, though, we're going to skip that piece, just because we know it's going to be positive and negative. This works as well when you have another number next to it. Before we do, though, let's think about this. We were able to split up the square root of negative 25 into I times the square root of 25. So it seems like there is a shortcut we can use. The shortcut is, instead of writing negative 5 times the square root of negative 9, we could always write this one out as just negative 5 times I times the square root of positive 9. Because remember, I would be if we pulled out that negative square root of negative 1. If we pull out the square root of negative 1, we would just get I. So you could split your numbers up like this and do the long way around. If this makes more sense to you, stick with it. It certainly makes more sense to me. But the shortcut is, hey, anytime you have a negative square root, pull out the I, and now you've got a positive square root again. Well, what is the square root of 9? The square root of 9 is 3. So this is negative 5 times I times 3. Well, hold on a second. Negative 5 and 3 can combine. Negative 5 times 3 is negative 15. So this is negative 15i. One more problem I want to show you is going to be letter C, and then I want you to try to see if you can tackle the other problems on the page yourself. For C, we have the square root of negative 72. Uh-oh. We've got a square root of a negative here. But we know, by our shortcut, this is just going to be I times the square root of positive 72. So you should always take out the I if you can. But the square root of 72 doesn't give us a perfect number. It's not a perfect square. So what can we do? Well, we have to use our little trick, splitting 72 up into two numbers, one of which is a perfect square. Well, we know one of them. We know that we can do 36 times 2 to get 72. And 36 is a perfect square. So this is I times the square root of 36 times 2. In other words, this is I times whatever the square root of 36 is, times the square root of 2. What is the square root of 36? It's just 6. So this is 6i. We treat I kind of like a variable in that it goes last in our number. Root 2. 6i root 2 is our answer. I want you to pause the video and I want you to try these other problems out. D is a lot like a combination of B and C. E is a lot like problem C. F is a challenge problem. I want you to try out F if you can. Do your best. But just know, it's okay if you can't get all the way done. My hint, try to simplify each piece. Pause the video here and try these problems out. Seriously, pause it and try them. It's good practice. How'd we do? For D, you can see I actually messed up the first time, but we got 6i times the square root of 6. For E, we get 4i times the square root of 2. And for F, we might have seen something like this when we started simplifying. But there are some rules I want to show you that we may not have learned before. For instance, if we have 5i here, and we have 7i here, how many i's do we have? Well, that's the same as just writing 12i. Of course, we would end up here with I times the square root of 16 times the square root of 3. And this is I times the square root of 25 times the square root of 3. So we end up getting 12i plus 4i root 3 minus 5i root 3. Interesting answer here. But then we see something very, very unique. If we have 4 I root 3's and subtract 5 I root 3's, we can actually combine these two terms. That's right. We're allowed to combine these terms if they have the same variable. So I here would be a variable for us, representing the square root of -1. And the square root of 3 here can also be combined. We end up with 12i minus I root 3, because 4 minus 5 is -1. Weird answers, but we're going to learn a little bit more about how we can combine these I values on the next page. So let's flip, and let's talk about these. Here's the deal. Before we start talking about how to add, subtract, multiply, and divide these imaginary numbers, we should talk a little bit about complex numbers. Like we mentioned, a complex number is when you combine a real number and an imaginary. So this would be a real part. This would be an imaginary part. And we can represent it with a plus bi, where a and b are real numbers. So, for instance, if we had a real part of 3 and an imaginary part of 2i, this would be a complex number. We can do this as long as we have a real piece and an imaginary piece, and as long as neither part is 0. Here's a diagram to show you a couple examples. Real numbers, when we don't have an imaginary part, are like -1, 5/3, pi. Imaginary numbers are when we have things like 2 plus 3i, 9 minus 5i. These are like our complex numbers. Pure imaginary numbers are another name for just the imaginary parts without a complex piece. We would say that these are when we have just an I part. If we want to solve problems with complex numbers, we have to remember that we cannot combine a real part and an imaginary part. That's why we have them separate up here. We have a real piece and an imaginary piece. When solving these problems, it's the same thing. We cannot combine, for instance, 2x minus 7i, because that's a real piece and an imaginary piece. We can't put them together. But we can put a real piece and a real piece together. Like, we have 2x and we have 10. So those are two real pieces that we can put together, right? And we have imaginary pieces, negative 7i and yi. So can't we put those together as well? The way we solve equations with two complex numbers is we can set the real pieces equal to each other, because a real can only equal another real. 2x should equal 10 here if we want these two to be the same. So let's just look at the real pieces. If we want 2x and 10 to be the same thing, we want them to be equal, what should x be? Well, to solve that, we can just divide both sides by 2, getting x equals 5. So we should get here that 2 times 5 is 10, and it does work. X is 5. We can do the same thing for the imaginary piece. If we have negative 7i equals yi, well, how do we solve for y here? We can treat I like a variable. So if we want to get y by itself, we can just divide both sides by I, by the imaginary number, square root of negative 1. Well, these cancel, and we're left with negative 7 equals y. So these are our two answers. X should be 5 to make 2x equal 10, and y should be negative 7, so that negative 7i is negative 7i. Perfect. Do you think you're able to solve these other ones? Again, pause the video and see how we do. How we do? Here, when we solve this one, we say x is equal to 9. Oh, that's just our answer. With this one, we have 3i equals negative yi. So in this problem, I showed you how you could do it piece by piece. You could divide out the I first, giving you 3 equals negative y, then divide by negative 1 on both sides to get y equals negative 3. However, in the next problem, I showed you how you could do it in one step. Let's look at the imaginary piece here. We end up getting negative 4yi equals 3i. So we wrote it down here in blue. Instead of dividing the I first, then dividing by 4, and then dividing by the negative, we can do it all in one step. We can divide by negative 4i. The i's cancel out over here, and we're just left with negative 3/4. Very nice. Talking about adding and subtracting complex numbers is a lot like adding and subtracting polynomials. The idea is this. When we're adding two of these complex numbers together, we can imagine it as if it was just 8 minus I plus 5 plus 4i. That's just plus 5 plus 4i. Well, negative I and 4i can combine, and 8 and 5 can combine. Again, we want to combine our real parts and combine our imaginary parts. So for the real piece here, 8 plus 5 is just 13. And negative I plus 4i is 3i. So our answer is 13 plus 3i. We just combine our real parts and our imaginary parts. When it's subtraction, though, it's a little bit different. Remember that when we're subtracting parentheses, it means we're subtracting 3 and we're subtracting negative 6i. The way I recommend doing this is if you have subtraction, you should distribute that negative and turn it into an addition problem. It makes it so much easier to deal with. So this would give us 7 minus 6i plus negative 3 plus 6i. Because again, we distributed the negative to both terms. Then we can just say we have 7 minus 6i plus negative 3, which I'm just going to write as minus 3, plus 6i. Oh wait, watch what happens to our imaginary parts here. 7 and negative 3 combine to make 4, but negative 6i and positive 6i, well, they cancel out. They make 0. So we end up with this complex number plus this minus this complex number gives us just a real number answer. You think you could try out C for yourself? Let's see if we can do C. Pause the video, try it out. How'd we do? 11 minus 2i is our answer because, again, we distribute the negative into the parentheses. This becomes negative 2 and minus 7i, giving us 11 minus 2i. Perfect. Let's flip the page. Let's talk about multiplying. Multiplying complex numbers is a lot like multiplying binomials. We've done this before in the past, but I want us to remember how we did it. So, if we're multiplying 4i times negative 6 plus I, the first thing we should realize is we should distribute the 4i. So now we have 4i times negative 6 plus 4i times I. Well, 4i times negative 6, we can just multiply the real pieces of these. 4 times negative 6 is negative 24. So this is negative 24i. But what's 4i times I? 4i times I we can write as 4i squared. Wait a second. Didn't we say we had a rule about 4i squared? I squared is just negative 1. So this is the same as writing negative 24i plus 4 times negative 1. Remember, I squared is the same as negative 1. That's what we said in our notes on this page over here. I squared is just negative 1. So, we know negative 4 and negative 1 multiply to make negative 4. So this is just 24, or negative 24i minus 4. We do want to write our answer in the standard form of a complex number, with the real part first and the imaginary part second. So our real part is negative 4, we should write the negative 4 first. And the imaginary part is negative 24i, so we should write that part after. Our answer is negative 4 minus 24i. Perfect. Now what if we have a problem like B? For B here, we have two binomials. So we have to remember how we multiply two binomials. There's a certain trick we learned in middle school called FOIL, F-O-I-L. The F stands for first. So we multiply the first two terms. What's 9 times negative 4? What's negative 36? What's 9 times 7i? Well, 9 times 7, that's going to give us 63, right? So 9 times 7i is just 63i. We did our first, we did our outer. Now the I in FOIL stands for inner, so we should do our inner two terms. What's negative 2i times negative 4? Well, negative 2 times negative 4 is positive 8. So we're left with positive 8i, right? So we have plus 8i. And then we should do our last terms as well. What do we have when we do negative 2i times 7i? Well, now we have negative 2 times 7, which is negative 14. But what's I times I? That's going to give us I squared. Interesting. Let's start simplifying. We know that negative 36 is just going to be our real part. That's going to stay at the front of our complex form. 63i plus 8i is 71i. So we have 71i here. Negative 14i squared, we say that I squared is the same as just negative 1. So it's negative 14 times negative 1. In other words, we get negative 36 plus 71i plus 14. Negative 14 times negative 1 is just 14. So we can put plus 14 here. And what's negative 36 plus 14? Well, it gives us our final answer here, negative 22 plus 71i. There we go. Very nice. This is our answer. Do you think you can try letter C? Try C by pausing the video and try it out for yourself. How'd we do? Did you see that we get 9 minus 6i minus 6i plus 4i squared? The two 6i's can combine to make negative 12i, and I squared is just negative 1. We multiplied 4 times negative 1 to get negative 4, and then we simplified. Perfect! Last but not least, we have the complex solutions and complex zeros. This is very familiar to us. We know how to solve a quadratic equation in 3 ways because we talked about it last section in 3.1. This time, however, we are going to get complex solutions. Now, we can solve these any way we want. You can solve them by, again, graphing, solving using square roots, or factoring. Of course, we have to decide which method is the most appropriate for this problem. So let's take a look at A here. A, we have x squared plus 4 equals 0. If I was to graph this, we would end up with something very interesting. We would end up with the following. This here is the graph of x squared plus 4 equals y. It's this way because when we do our vertex, our negative b over 2a, our axis of symmetry is going to be 0. So we know our vertex is going to be at 0. We plug in 0 for x, we get 4. So this is where our vertex is. What's wrong with this? Why can't we find solutions here? It's because solutions are where our graph crosses the x-axis, and this graph doesn't. If you have a graph that floats above your x-axis, we know that it's going to have imaginary solutions. There are ways to figure out what the imaginary solutions are from a graph that floats up. We're not going to talk about those because, unfortunately, that's a much more advanced technique than what we're going to be talking about in this unit. Instead, if you end up with a graph like this using the graphing method, my suggestion is try a different method. We can't factor this, but we can solve it. So if we, for instance, subtract 4 from both sides, we would end up with x squared equals negative 4. What do we do to both sides to get x by itself? Well, obviously, we would need to square root both sides. When we square root x squared, we just get x. But the square root of negative 4, of course we want a plus and minus version. Plus and minus the square root of negative 4 is an imaginary answer. Well, what is the square root of negative 4? That's the same as plus or minus I times the square root of 4. Because again, we can take the I out to make our square root positive again. That leaves us with our answer. Because the square root of 4 is just 2, we get positive 2i and negative 2i. These are our two solutions. They're not real roots, but they are imaginary roots of x squared plus 4 equals 0. We can solve these algebraically to find our zeros. Try doing it with this problem here. This is going to be a little bit tough, but I think we've got it in us. Try out this problem here, pause the video, and come back and we'll talk about this. How did we do, everyone? Did we get plus or minus 3i times the square root of 2? Again, this works because when we start doing algebra, simplifying bit by bit, we're square rooting negative 18, so we can take out the I and put it in front. The square root of 18, for those who are curious, is just the same as the square root of 9 times the square root of 2. And the square root of 9 is just 3. So that's 3 root 2 times I, or 3i root 2. Last but not least, we have 3 graphs, 3 functions. And we want to figure out which of these functions, h, f, and g, have real zeros, and which ones have imaginary roots. Well, we mentioned before, if we have a graph that's floating off of the x-axis, we say that its roots are imaginary. You see how h is floating up here, and it never touches the x-axis? It means there are no real roots, but we do have some imaginary roots. In this case, it would be I times the square root of 3, or plus or minus I times the square root of 3. Here, for f, we see that the graph f touches the x-axis once. If we have a graph that touches the x-axis once, we say it has just one real root. It has one real root. And since it touches at the origin, we say it has one real root, x equals 0. Finally, for g, this looks like the type of parabola that we would see in section 3.1. G, we have it touching twice. So there are 2 real roots, and we don't quite know what they are because we don't have the equation of this parabola. However, you could figure it out. So here's a challenge question for you. Based on this graph, could you figure out the equation of this parabola? And if you can you then solve for the roots. I'll leave that one to you, but here's a hint. This graph has a real point here at 5, 5. So now we have a vertex and a point. Now we can make an equation. I'm not going to ask you to try this one out. This is a very challenging problem, but come talk to me if you think you have an answer. With that said, everybody, that is the end of section 3.2. If you have any questions, feel free to ask. Otherwise, have a fantastic rest of your day.